Hello everyone, this is the video for topic 8.1b. We're going to talk about the standard normal curve. We are going to revisit the normal distribution, but this time we are going to standardize it. Now, the reason why we want to standardize our normal curve is we want to figure out how far the value is from the mean, or you want to ask yourself how different are these two statistics. So sometimes you may want to compare an ACT score to an SAT score because those are two different tests. They have different averages and different scales, and it's really hard to tell if one person did better or worse than the other one without, being able to standardize the score. Basically, what happens when you standardize a normal curve is you're able to put it in units that are comparable. Actually, a standardized normal curve or a z-score doesn't have any units at all, and that's why you can actually compare it. It's kind of the same concept when you were in elementary school and you were trying to compare something like 4/5 to 9/11. You're trying to figure out what's going on. You don't know which one's bigger than the other one until you actually get it to where you have the same unit or the same denominator. So in this case, your denominator would be 55, and then 5 goes into 55 11 times, so that would be 44. So 44 out of 55 is the same thing as 4 out of 5, and then this one up here would be 45. Now these are awfully close to each other, but until you change it, you can't realize, you don't see that this 44 is actually less than 45. So here you don't know, but here you know for sure. Same concept, we're just doing it with normal distribution. So let's do a little bit of exploration before we get into the actual formulas for the day. So it says, looking at the normal curve to the right, you have 1.85 is 3 standard deviations from the mean of 1.4. So let's see if we can find where 1.85 is. It's right here, and I say that it's 3 standard deviations because this would be +1, +2, and +3. Okay. Now, if it's 3 standard deviations above the mean, it's going to have a z-score of 3.0. Why? So let's calculate it. Let's go through the process of calculating what a z-score is. So it's possible to calculate how many standard deviations you have from the mean. So this is going to step you through it in words. How far is 1.85 from the mean? So when it asks how far, you can just subtract 1.85 from the mean. Now in this case, the mean is 1.4. So I'm going to say 1.4. I'm going to go the right direction, sorry. 1.85 minus 1.4. So you're going to take the value right here and subtract the mean. So value minus the mean. And that's going to give you 0.45. So that is the distance to the mean. Okay, one more step. How many standard deviations is that? So if you want to figure out how many standard deviations it is, mathematically, you're going to take the distance from the mean, and we're going to divide it by the standard deviations. And the standard deviation, they tell you right here, is 0.15. So if you type that in your calculator, that is exactly 3. So basically what it is, you've got the distance divided by your standard deviation. So that is going to be 3, and that's how you get a z-score of 3. And if it's positive, it's going to be above the mean, and if it's negative, it's going to be below the mean. Okay, so let's talk formulas. The z-score is exactly how many standard deviations a value or a data point is from the mean in a normal distribution. So if you look at this visual aid over here, we have a normal distribution, and it says normal distribution, and you've got the mean in the middle, and you have +1, 2, 3 standard deviations to the right, and you have -1, 2, 3 to the left. But what you can do is you can change each one of these numbers into something called a z-score. And these are z-scores. And I did a little bit of this in the last lesson. Your mean, on the other hand, since it is exactly where the mean is, there's no standard deviations away from the mean, it's going to be 0. Anything above the mean will have a positive value. If it's exactly on the line, it will be +1 or 1 standard deviation away, 2 or 3 standard deviations above the mean. If it's negative, it's going to be below the mean. So -1 standard deviations, 2 or 3. So anytime you say +1 or -3, that is exactly a standard deviation measurement, and that is the z-score. So you've actually been using z-scores and you haven't even known it yet. I do want you to notice, though, if you change it to 0, 1, 2, 3, this is now called the standard normal distribution, okay? The standard normal consists of z-scores. The normal distribution is the original data values. And just to reiterate why we use a standard normal distribution, we would either want to compare sets of data that have different means and standard deviations, or we want to just figure out where a value is in comparison to the mean. Okay, so let's get to the formula. So above this, at the beginning of your notes, it actually had you find the value minus the mean, and it divided by the standard deviation, which gave you your z-score. This is what it looks like on your formula sheet. It is in words. It does not use symbols, which is awesome, but you do need to know how to use it and why you're using it. Something else that's really important is that z-score values have no units. So if something starts in feet or inches or, I don't know, like points on a test, when you convert it to a z-score, it has a number value, but it's no longer in points or whatever. It's just that many standard deviations away from the mean. And this just kind of reiterates what I said earlier. Negative z-scores are going to be below the mean, and positive z-scores are going to be above the mean. So what happens when we standardize? Remember, if you find a z-score, you're finding the location of the data point instead of the actual value, because you know the value of the data point. So if you have a z-score of 0, a z-score of 0 is literally in the middle of the data. It is the mean. If you have a z-score of +1, it's going to be exactly 1 standard deviations, but since it's positive, it's going to be above. And if it's negative, it'll be that number of standard deviations below the mean. And then one last tidbit of information before we do some practice problems. Generally, a z-score of 3 or greater or 3 or less is considered to be very unusual. And the reason why is that less than 1% of your data is going to be hanging out in that zone. So if you have a z-score of less than 3 or greater than 3, it's less than -3 or greater than +3. It's really special. It's very, very rare and very unusual data. Okay, so I went ahead and labeled this. This is, you should be able to do it. It's from the last lesson. It tells us that we have a mean of 38.8. And we have a standard deviation of 11.4. So I just used my calculator and I added 11.4 to the mean. And I continually did that again and again. And then over here, you take away 11.4 again and again. So what we want to do is we want to convert this to a z-score. So 26. Now, do you see 26 anywhere on this? You don't, okay? If I asked you what the z-score is for -16, that would be pretty easy because your mean has a z-score of 0. This would be -1, and that would be -2. So 16 would have a z-score of -2. Why? Because it is 2 standard deviations below the mean. So since we don't see 26 on this, I can't just like visually, figure out the z-score. So what I'm going to do is I'm going to find the distance. So the z-score formula says take your value or your data point, which is 26, and then you're going to subtract it from the mean. Now the mean is 38.8, and then you're going to divide that by your standard deviation of 11.4, and then we're just going to type that on our calculator and see what we get. Okay, so I showed a little bit of my work because I wanted to make a point. This top part right here is negative. That is the distance from the mean. So if that distance is negative, that means that your value was on the left-hand side of your mean. So when you divide it by 11.4, that tells you how many standard deviations it's going to be from the mean. So it's going to be on the left-hand side because it's going to be a little bit past the 1, the negative 1 right here. So 26 should be about right here. And if you look at that data, it makes sense. So the second part of the question is just asking you how many standard deviations 26 is from the mean, and we just found the z-score. So we just need to write in words what that z-score means. So 26 is 1.12 standard deviations. Now here's where you need to use your positive or negative. So since it's negative 1.12, we're going to say below the mean. That's all you got to do. Okay, I really like this example. It talks about how as a college admissions officer, you're going to have to look at lots and lots of different applications. Students have taken different tests. For example, some of them have taken the ACT and some of them have taken the SAT. And those are two completely different tests. Where we are, we typically take the ACT and the SAT is optional. So if you guys are interested in the SAT, you can take it. You just have to pay for it. So what it does is it asks you to make a decision about two applicants. Everything seems to be about even, and you're going to have to look at their test scores to make a decision. So I'm going to highlight student A in blue. Student A took the ACT and received a score of 29 in math. Now student B, I'm going to highlight in green. Student B took the SAT and received a score of 680 in math. So you can see that the ACT has a score of 29 and the SAT received a score of 680. Now it's going to tell you a little bit about both. It's very important that it mentions that both tests are normally distributed. If they weren't normally distributed, you wouldn't be able to standardize it using a z-score. Now, the perfect ACT score is 36. That's information you don't necessarily need. What you do need is the mean and the standard deviation. And it does tell us this. It says it has a mean of 21 and the standard deviation is 5.3. Now, you don't have to do a full picture of it, but I do want you to see what it kind of looks like. I'm just going to label the mean. So the mean is 21, and then on the outside, I'm going to say the standard deviation is 5.3. So it's got a very small standard deviation, and this is going to represent student A. Okay. Now, student B took the SAT, and it is also normally distributed, and the mean of the SAT was 516 with a standard deviation of 116. So much larger variance in this case. So 516 and the standard deviation is 116. So it's really, really hard to tell. I know that both of them are above average, but we want to know how far away the score is from the mean. And that's going to tell us which one actually did better. All right, so I'm going to find the z-score of each of the particular ACT scores. So in this case, they made a score of 29 on the ACT, but on the SAT, they had a score of 680. So both are really, really good. So we're going to take our value of 29 and subtract the mean, which is 21, and divide by the standard deviation. So follow it very closely to your formula. The top part is the distance. So there's 8 points to the mean. And now when you divide, that's going to tell you how many standard deviations away it is. So on your calculator, we're going to do 8 divided by 5.3. And we get about 1.51. Typically, z-scores are 2 decimal places. On the SAT, this person had a score of 680. We're going to subtract the mean, which is 516. We're going to divide by the standard deviation. So the top part is going to give us the distance, which is 164. So positive, that means it's above the mean. Now I'm going to figure out how many standard deviations that is by dividing by 116. That is 1.41 standard deviations above the mean. So they are both clearly above right here. So they have a good score, but which one is better? Okay. Now that I have a standardized normal distribution, remember the standardized one, the mean is 0. Where's the ACT score? So the ACT is 1.51, but the SAT is a little bit less than that. They're very close. Okay, but which one's better? This one. This one's a little bit further away from the mean than the SAT one. So the best thing is go ahead and give that scholarship or let that person into the college. They just barely beat out student B for that position. Okay, so example 3. I don't have a lot of room, so I'm just going to do this right here. I'm going to make a big chart. So it says that Jack's z-score was 1.49. Where is 1.49? So this is 1, 2, 3. So 1.49 would be about here, okay? So that's 1.49. That's the location of Jack's score. Now, Jill's score was 0.89. So this is 1. So 0.89 is a little less than 1. So 0.89. So this is where Jill is. Now, the question is, did Jack or Jill do better on the test? Now, they both did better than the mean, right? But which one is further away from the mean? Jack. So I think Jack did a little bit better on the test than Jill because the z-score was greater. Now, this last question right here is really important, okay? Sometimes it doesn't give you the actual value and you have to work backwards, all right? So if it says the mean of the test, let's take some notes. The mean of the test was 76 and the standard deviation was 6.3. Now you got to go backwards and you got to find out what their actual scores were. These are standardized scores. They didn't make 1.49 points or 0.89 points. That's just how far away it is from the mean. So what you're going to do is you're going to take your formula, okay, your z-score formula. So the value or your data point minus the mean divided by the standard deviation. Okay. So I'm just trying to write that as fast as I can. So let's do Jack's score first, and then we'll do Jill's score next. Okay, Jack's z-score was 1.49. So it's going to be equal to the z-score. What we're trying to do is we're trying to figure out what his actual test score was. The mean of the test was 76. And the standard deviation was 6.3. Okay, so this is what we're looking for. This is different. This is backwards. So we're going to use inverse operations. First thing you want to do is get rid of the 6.3. So I'm going to multiply by 6.3. We get 9.387. Don't round unless you have to. Okay, and then we're going to finish it up by getting x by itself. We're going to add 76 to that. And that's going to be 85.387. Now we're talking about test grades. So if we're going to round it to the nearest point, I'd say that he made an 85. Let's do the same thing for Jill. Now, this is the same test, but Jill had a different z-score because she performed a little bit less when compared to Jack. She still did really well. She was 0.89 away from the mean. We're looking for the value of the test. We're going to subtract the mean of 76, same standard deviation. So the good news is we're going to do all the same steps, and we get 5.607. And then we're going to finish up by adding 76, and we wind up with 81.607. Now, if we've done this correctly, Jill's score should be just slightly below Jack's score. We're around that to an 82, and that makes sense, doesn't it? So if we had a mean of 76, you can see that Jill did a little bit better than 76, and Jack just a little bit better than Jill's score. And that's how you work backwards. Let me know if you've got any questions, and have a great day.